Our entire galaxy is being pulled through space at over 2 million kilometers per hour towards something massive we have never directly seen. Because it sits behind the one part of the sky our own galaxy refuses to let us look at. We can measure the pull precisely. We can point to roughly where it comes from, but the thing itself stays hidden, blocked by the only obstacle big enough to hide it: the Milky Way. Stand outside on a clear night and everything feels still. It isn't. The Earth turns and circles the sun sweeps around the center of the galaxy, and the whole Milky Way is moving too. Not just expanding outward with the universe, but drifting in one particular direction, faster than the expansion alone can explain. That extra motion has a name: our peculiar velocity. And we can measure it against the most even backdrop in existence: the cosmic microwave background, the faint afterglow of the Big Bang. Because we are moving through it, that glow looks very slightly warmer in the direction we're heading, and cooler behind us. From that tiny lopsidedness, astronomers read our speed. Roughly 600 kilometers every second, give or take. This part is solid, measured, repeated, agreed upon. We are not sitting still in the cosmos. We are falling steadily toward something. In the 1980s, a team of astronomers mapped how hundreds of galaxies around us were moving, and found they weren't drifting randomly. Whole swarms of galaxies, including our own, were streaming the same way, toward one region of the sky in the direction of the constellations Centaurus and Hydra. They called the unseen cause the Great Attractor. The group became known half-jokingly as the Seven Samurai. Their best estimate placed it somewhere around 150 to 250 million light-years away. A concentration of mass, thousands of galaxies worth, tugging on everything nearby, including us. But here's the first honest caveat. The Great Attractor's exact mass has never been pinned down. We see its gravitational effect clearly. The size of the thing causing it, that stays uncertain. And there's a reason it stays uncertain. To look toward the Great Attractor, we have to look straight through the most crowded part of our own galaxy. The dense band of stars, gas and dust that forms the Milky Way across our sky. That dust absorbs and scatters light. So in visible wavelengths, roughly a fifth of the entire sky is simply blocked from view, a permanent curtain drawn across the cosmos. Astronomers call it the Zone of Avoidance. The thing pulling our galaxy sits almost directly behind that curtain. This is the heart of the whole mystery, and it is a verified physical limit, not a guess. We are trying to study the strongest pull in our corner of the universe, and our own galaxy is standing in the way. Radio and infrared telescopes can pierce some of the dust, and they've found galaxy clusters hiding back there. But the view is partial and incomplete to this day. Then the story deepened. As surveys reached further out, past the Great Attractor, they found something larger still. Far beyond it, around 650 million light-years away, sits the Shapley Supercluster, the most massive concentration of galaxies in our cosmic neighborhood. And much of the pull we feel may actually be coming from there, with the Great Attractor sitting partway along the same line, like a nearer hill in front of a distant mountain. How much of the pull is the Great Attractor, and how much is Shapley beyond it? That split is still debated. The leading view gives Shapley a large share. But the exact budget, hidden partly behind the Zone of Avoidance, is not settled. And then, in 2017, came a genuine twist, one that flips the intuition entirely. A team mapping the flows of thousands of galaxies in 3 dimensions argued that we aren't only being pulled toward dense regions, we are also being pushed away from a vast, unusually empty region of space behind us. They named it the Dipole Repeller. The idea is counterintuitive but follows straight from gravity. An emptier-than-average region has less mass than its surroundings, so relative to everything else, it effectively pushes matter away. Pull from the dense side, push from the empty side, both nudging us the same way. Mark this carefully. The Dipole Repeller is strongly supported by the flow data. But it is not universally settled, and the push versus pull balance remains an active question. So let's be honest about where the knowing ends. We know our speed, 600 kilometers a second, measured cleanly against the afterglow of the Big Bang. We know roughly which way we're going. We know the Zone of Avoidance hides a fifth of the sky, and that the strongest pull sits behind it. But the full accounting, how much is the Great Attractor, how much is Shapley, how much is a void pushing from behind, that ledger is still open. We are being carried across the universe by forces we can measure but cannot yet fully see. If you like your wonder honest, what we know kept separate from what we only suspect, there's a free one-page guide in the description, because the best part of the universe isn't the part we've solved. It's the edge, where the knowing ends and the awe begins.